Every single time you wash your hands or flush a toilet, you're tapping into this incredibly complex, totally invisible network. It's honestly one of the most critical systems in any building, but we never see it. So today, we're going to pull back the curtain and uncover the hidden science of plumbing design. I mean, it seems so simple, doesn't it? You just turn the handle and poof, water comes out. But behind that one simple action is this amazing feat of engineering. We're talking a whole series of precise calculations, all designed to give you the exact amount of water you need at just the right pressure every single time. So what is really going on behind those walls? Okay, so to really get a grip on a building's plumbing, it actually helps to think of it like a living, breathing thing. We're about to dive into this hidden network that works, well, it works almost exactly like the circulatory system in your own body. The pipes are the arteries, and the water, that's its lifeblood.
And it's such a perfect analogy, right? Just like our veins and arteries move blood around, a building's pipes are busy bringing clean water in and taking wastewater out. It's literally the lifeblood of the entire structure, making sure every single part gets exactly what it needs to work properly.
So this whole circulatory system is basically made up of 5 key parts, and they all have to work together perfectly. You've got your cold water supply coming in, then you've got the hot water system that heats it and sends it where it needs to go. Then there's the drainage, which gets rid of all the waste. The vents are super important too. They help the drainage flow right. And finally, the big one, the pumps and tanks that are the muscle behind the whole operation. All right, so imagine you're a plumbing engineer. Your first and probably biggest challenge is, well, it's basically predicting the future. You have to figure out how much water a building is actually going to use. To crack that problem, you've got to learn to speak what you might call the language of water. No, seriously, think about it for a second. In some giant building with hundreds of faucets, showers, toilets, how on earth could you possibly predict how many of those are going to be running at the exact same time? It seems totally impossible, right? Just a wild guess. But here's the thing. Engineers don't guess. They calculate. And the way they do it is with this absolutely brilliant concept called the fixture unit, or FU for short. It's such a simple idea, but it elegantly solves this super complex problem. So instead of guessing, every single thing that uses water, your sink, your toilet, your shower, gets assigned a standard number. It's like a universal language for plumbing design. And the method itself is beautifully simple. Step 1, you just go through and count every single fixture in the building. Step 2, you give each one its standard FFU value, which you get from the official building codes. And then step 3, you just add them all up. That's it. And that one single number you're left with, that represents the building's absolute maximum potential water demand. And here is where it all comes together. That total fixture unit number isn't just an abstract value. You take that number, look it up on these standardized charts, and it converts directly into a real-world design flow rate. We're talking a specific number, like cubic meters per hour, that the system absolutely has to handle during peak use. And just like that, problem solved. Okay, so that's a huge piece of the puzzle, right? We now know how much water the building needs. But believe it or not, that's only half the battle. Now we've got to figure out how to get it there. We have to design the arteries and veins. This is all about sizing up the flow. And let me tell you, sizing the pipes is a really delicate balancing act. It's a classic Goldilocks problem. If the pipes are too small, you get all kinds of problems. High friction, that awful noisy whining sound on the walls, and the water moves way too fast, which can cause damage. But if you go too big, well, you're just wasting a ton of money on materials. And worse, the water moves so slow it can stagnate. It's got to be just right. So here's the key takeaway. Every single piece of the system, every foot of pipe, every little elbow joint, every valve, it all creates resistance. It fights back against the water. The entire design process is basically a battle to get water where it needs to go, all while fighting this constant invisible enemy called friction loss. So how do you win that battle against friction? And how do you lift all that water multiple stories up into the air? Well, the system needs power. It needs a beating heart. And that, of course, brings us to the pumps, the real engine driving this whole network. Now, to pick the perfect pump for the job, engineers have to calculate something called the total dynamic head, or TDH. I know it sounds super complicated, but it's actually not that bad. It's really just a fancy term for adding up all the different challenges the pump needs to conquer to get the job done right. So let's break it down. The first piece of the puzzle is called static head.
And this one's the easy one, really. It's just the physical, vertical distance the pump has to push the water upwards. So in the example we're using, this 2-story villa, that's a lift of 9 meters, from where the pump sits all the way up to the highest shower head.
Next up, we have to account for that enemy we just talked about, friction loss. Remember all that resistance from the pipes and all the little fittings? Well, it all adds up. For this villa, the engineer crunched the numbers and figured out that overcoming all that friction is the same as having to lift the water an extra 7 meters. And last but not least, you need the water to actually come out of the faucet with some oomph, right? Nobody wants a sad little trickle from their shower. That's called residual pressure. The system has to guarantee a minimum amount of force right at the fixture, and in this case, that requirement is equivalent to pushing the water another 15 meters higher. And there you have it. You just add those 3 numbers together, you've got 9 meters for the actual height, 7 meters to beat the friction, and 15 meters to make sure the pressure is good at the tap. So the pump we choose has to be strong enough to overcome a total dynamic head of 31 meters. That's our magic number. Okay, so we've talked about all these kind of abstract ideas: fixture units, friction loss, total dynamic head. Now, for the fun part, let's see how it all comes together to create a real working system inside a typical family home. See, we've actually been using the numbers from this 2-story villa this whole time. So now, let's look at the final specs, what all that careful math actually translates into. So check this out. This is pretty much the final blueprint. Our fixture unit math told us we need a flow demand of 2.5 cubic meters an hour. Then our TDH calculation gave us that 31 meter number. So what do? We pick a pump that's a little bit stronger, in this case, one that can handle 32 meters of head at 3 cubic meters per hour. That little bit of extra power is what guarantees you'll have great pressure even if a couple of showers are running at once. See, every single part here, from the pump to the tank size to the pipe diameters, is chosen based on solid calculations, not just guesswork. And that's really the magic of the whole thing, isn't it? You start with something so simple, just counting up toilets and sinks, but that leads to this chain of calculations that ends with a perfectly chosen pump, pipes that are exactly the right size, and a whole system that just works, flawlessly and silently, right there behind your walls. So maybe the next time you turn on the tap, you'll think for a second about the really elegant science that's making it all happen. It kind of makes you wonder, doesn't it? What other invisible, absolutely essential engineering is quietly powering your world every single day?